Hello everyone. In this lecture, I would like to talk about one of the topics that we discussed in lecture 2, but apparently it was not very clear. Some of you asked some questions and I would like to clarify them. In particular, we want to talk about statically equivalent system of forces, and specifically this one slide. So in this slide, we had a lot of information covered and I want to talk about that a little. I will mostly talk about the first row of the slide, and I think that would be enough. So we said that we can define statically equivalent system of forces, and the requirement for different systems to be statically equivalent was that the resultant moment in all these equivalent systems must be the same, and the resultant forces in all these equivalent system must be the same. Okay, so the idea is two systems are equivalent if they have the same resultant force and the same resultant moment. Now in this example, we assume that these three pictures are statically equivalent. You can basically see that the force in each of them is exactly the same force, so the same magnitude, the same direction. So the resultant force in all of these pictures is just the force F. They are equal. So in terms of the force F, they are identical. Now, how about the moment? We want to study that. We want to know what we can say about the moments of these systems. In the first system, if you write the moment with respect to A, and that would be the resultant moment, so this is essentially resultant moment about A, or with respect to point A. So if you write that, it would be 0. Again, it's not about equilibrium, it's just the resultant moment with respect to point A is 0, or any other point along the line of action of F. So we want to do exactly the same thing for this picture. We want to write the resultant moment with respect to point A. And I suggested if you shift the force F from point A to point O, then you would need to introduce a new moment into the system to keep the systems equivalent. We want to analyze that suggestion a little more. So the moments, the sum of moments or the resultant moments, the resultant moment in this picture, it would be AO cross product F plus the additional moment that I suggested it would be required for the two systems to be equivalent. Now for the two systems to be equivalent, the requirement is that they must have the equal resultant moment. The resultant moment of the first system was 0. That means the resultant moments of the second system with respect to point A must be also 0. So having said that, it essentially tells you that you need the moment with respect to point O, or moment minus AO cross product F. You need that much moment added to the system to ensure that the two systems are statically equivalent. We can play exactly the same game with the third picture. So with the third picture also you can write the moment or the sum of moments with respect to point A. If you do that, now your arm would be AO prime, and then the cross product of that with the force would give you a moment. So this gives you the moment of force F with respect to point O. But then again, remember, with respect to point O, you should not have a moment. For that matter, you would need to add something to the system such that you keep the systems equivalent. And basically, by setting the resultant moment with respect to point A to be 0, again, also for this system, this gives you exactly this equation. So it tells you that MO prime is minus AO prime times F. So again, you see in both cases, you get, so in this case, you get essentially for that moment, you get this R, so AO times F with a minus sign. In this picture, you get this arm, so again, AO prime times F with a minus sign. So you can imagine for any other point B, if you wanted to just shift your force to any other point B, you need to add that much moment to the system, and that would be minus AB times F. Okay, so I think this should be kind of clear, or more clear than the previous lecture that we had. If you have different systems, you can call them statically equivalent if they have the same resultant force and resultant moment. And these three systems that we have here, these are statically equivalent based on what we just said. So what I want to do next is to choose a different point in the system to carry out the same study. So this was point A in this slide. Now we want to do exactly the same thing, or we want to play the same game, but we want to write the moments with respect to O prime. And then again, ideally, we should get exactly the same answer as we get now. Let's see what happens. So in the first picture, if you write the moment, and then again, this is the resultant moment. If you write the resultant moment with respect to O prime, that would be O prime A times F. So this is the resultant moment with respect to point O prime. In the second one, if we want to write the resultant moment with respect to O prime, that would be O prime O times F, plus the additional moment MO that we need to keep the two systems in equilibrium. If you don't add that to the system, then the two systems are not in equilibrium, because you can see the moments would be different. So to impose equilibrium, or to impose equivalence between the two systems, you need to say that the sum of moments, or the resultant moment with respect to O prime in the second system, is equal to the resultant moment with respect to O prime in the first system. That essentially means that the left-hand side must be O prime A times F, and if you insert that, you would end up with this equation. So O prime A times F equals O prime O times F plus MO. And then if you do the math, so you basically bring this to the left-hand side, then you would see that MO would be O prime A minus O prime O times F, and that is nothing but OA. So essentially MO, from this slide, we can see that MO is OA times F. So this is the moment that we need to add to keep the two systems equivalent. Or we can say this is minus AO times F. So keep that in mind. Essentially, from this slide, we learned that MO is minus AO times F. And if you remember what we had previously, it was exactly the same thing. So MO, whether you write the moments with respect to O prime or whether you write the moments with respect to O, MO, the amount of moment that you need to add when you shift a force to a different point, is calculated by this formula. You can play the same thing with respect to O prime now, but with respect to O prime, it's kind of easier because the arm is 0. So the only moment that you get with respect to O prime, the resultant moment, would be just MO prime itself. And then in order to make sure that these two systems are equivalent, you know that must be equals to O prime A times F, which you can also write as minus AO prime times F. And then again, this is exactly what we had from the previous analysis. Okay, so if you just remember these two, so that this is MO and this is MO prime, and I can show you what we had from the previous study. We had exactly this one when we wrote the moments with respect to A. So you can see that these two equations, they are exactly the same equations, the same answers essentially. Okay, so this was pretty much it. I think this should be clear now, and then you can think of that for simpler systems as we have shown here. So for instance, if you think about this system and then you want to write the moments with respect to a point here, let's call it point B, you can see that you have a moment due to the force with respect to point B. Now, if you shift the force a little further to the left or to the right, then you change that moment. And you need to add that much moment to your system to keep the two systems equivalent. So again, the two systems are equivalent if the resultant force, let's say system 1 and system 2 are equivalent, if the resultant force in the two systems are equivalent, and if the resultant moments in the two systems are equivalent. Okay, so you need to have both of them to call two systems equivalent. I hope this clarified the question that some of you asked.